Hello and welcome to N24, continuing with covalent bonding, but our focus is sigma and pi bonds. So our types of bonds, sigma and pi. A sigma bond results when the interacting atomic orbitals point along the axis connecting the two bonding nuclei. What the heck does that mean? So a sigma bond, also known as a single bond, so two electrons, exists between the two nuclei. So two atoms on either side, it is right in between them. Imagining that you're shaking hands with another person. You shake hands with each other about tummy waist height, if you will. So it's right in between the two atoms. Now, the atomic orbitals or hybrid orbitals that make up the sigma bond can be S to S, a P to another P, hybrid to hybrid, S to hybrid. Basically, any two orbitals that can be used, not the Ds or the Fs, but any combination of these S, P, and hybrid orbitals can make that bond that exists in between two bonding nuclei. And I'll have some images coming later to show that. On the other hand, we have pi bonds. These result when bonding atomic orbitals are parallel to each other and perpendicular to the axis connecting the two bonding nuclei. So they are not in between the two atoms. They are above the atoms and below. They are in front of and behind. I know, kind of hard to see that, but again, I'll have some images to show that as well. Pi bonds can only be created with unhybridized p orbitals. So kind of a big difference here with sigma and pi. Sigma, any combination of sp and hybrid orbitals, but pi bonds are only hybrid. Again, it's the type of orbitals that create these bonds, and secondly, it's the location of these bonds that matter. The interaction between parallel orbitals, pi bonds, versus the interaction between orbitals that make up a sigma bond tell us the difference in their strength. Sigma bonds are much stronger than a pi bond comparing to each other. Now, obviously, we get a double bond or a triple bond. That's a very, very strong bond as a total type of bond. But if I'm looking at a sigma compared to a pi, sigma will be stronger. Any questions on these two things? Okay. So, again, reiterating, sigma bonds exist in the region directly between the atoms, and pi bonds exist above and below, in front of and behind. Again, images to come. So when we try to figure out the number of sigma and pi bonds that exist, because that's a question that shows up on the AP exam, they give you a diagram of a molecule and ask you how many of each. Single bond is just sigma. A double bond is sigma and a pi bond, and a triple bond is a sigma and two pi bonds. Questions on the types of bonds in relation to sigma and pi? Okay, so an image, here's our single bond, sigma, single, same thing. It's between the two nuclei of the carbons. Now we get to a double bond. The sigma bond is still in between, but the overlap of the p orbitals, the unhybridized p orbitals, is what kind of makes up that pi bond. Now, I know this looks like there's three things on the screen, but you got to realize that this pi bond, this is one entire pi bond, as the orbital overlap exists both above and below at the same time. Questions on this image? Okay. From a triple bond perspective, yeah, I know, getting a little crazy. Now you can kind of see we still have our sigma bond right here, the solid line in between the two carbons. And then we have a pi bond above and below. Right here and right here is your above and below. But then we have in front, and this one over here is behind or going into the screen versus coming out of the screen. So yes, it looks like there's 5 things going on here, but in actuality there's only 3. The sigma bond and 2 separate pi bonds. Questions? Okay. So the thing we got to realize, p orbitals have this lovely shape of a pedal or a dumbbell. When you take 2 separate p orbitals and make a pi bond, as we can see here on the right, you can see that they overlap above and below the axes between the 2 nuclei. That's what we're getting, the above and below. So those 2 electrons in the top right image can travel anywhere within, excuse me, anywhere within that red area or the overlap of orbitals. The bottom diagram, we have 2 unhybridized p orbitals. They can overlap together to make a sigma bond because, again, they're in between the 2 nuclei. Questions? Okay. So here's our lovely crazy diagram, or one of them at least. So we can see we have the carbon on the left has hybrid orbitals, sp3 hybrids, sp2, sorry. And the oxygen on the right has nothing hybridized. So we already said a hybrid orbital and a p orbital can make our sigma bond in between the 2 nuclei. But then the carbon has 1 unhybridized p, and the oxygen also has an unhybridized p. Call it on the y-axis, for that matter, where the sigma bond is on the x-axis. If we look on the y-axis, there is our pi bond. This whole red area going above and below the plane gives us our pi bond. Questions about this one? Okay. So, orbital diagrams of bonding. The overlap of atomic orbitals end up making our molecular orbitals. And in this example, as we're kind of seeing below, again, we have a hybrid orbital with an unhybridized orbital, and then the overlap of the unhybridized p and another unhybridized p gives us our pi bond. Questions on this one? So continuing along, again, still looking at the same example that, again, just kind of making sure we're all clear on what atomic orbitals are overlapping in order to make both sigma as well as pi. Again, you put 1 sigma and 1 pi bond together, you get your double bond. Questions? All right. Well, here's the fun one to try and look at. Again, both carbons are sp hybridized, and the sp hybrids are along the x-axis, and they're making the sigma bond. Then you have an unhybridized p orbital on both carbons in the y direction, going above the plane and below the plane. Thirdly, you have an unhybridized p orbital on both carbons that is on the z-axis, this one coming out of the page and this one right here going behind the page. So the challenge here is realizing that p orbitals, because they are double lobed, they exist on both sides of the axis. So, a positive y and a negative y, a positive z and a negative z. Questions on this? Okay. We mentioned the localized electron model back when we talked about dot structures, and we mentioned the whole delocalized idea. These delocalized electrons have the ability to move around freely. We saw benzene last time. Here's our two resonant structures on the left of benzene. The structure on the right, the two green tubes, if you will, represent the one unhybridized p orbital on every single carbon. So all 6 carbons in benzene are sp2 hybridized, but they have one unhybridized p orbital. Therefore, all of those unhybridized p orbitals for every single carbon, they all kind of blend together. And because they blend together, they give us this one huge connection, the green tubes that you see, above the plane and below the plane of the of the actual molecule. So the electron density enables it to kind of free flow above and below. That's why the electrons are moving between double bonds in one place versus double bonds in a different place. So these tubes, these rings, it's all just unhybridized p orbital electrons that are all blending together. Again, not hybridizing, but blending together in their overlap in order to allow those p electrons to move freely within the molecule, and they are delocalized. They do not belong to one carbon or another carbon. They're free to move. Questions about this? Okay. Thank you very much.